Welcome to the Rory Academy YouTube channel. We share valuable information about power electronics technology and its emerging applications. We have a great announcement to make. Coming soon, we will launch a platform for power electronics technology-based developers. Introducing the brand new www.roryacademy.com. This will be a first online platform where the design, development, and prototyping of power electronics-based systems and products will be learnt and ideas shared through on-demand courses, webinars, tests and evaluation kits developed and sold, and a forum for the curious minds. All our YouTube subscribers will have access to 1-year free membership, which attracts 10% discount on all products. Remember, think deep, think beautifully. This video provides an in-depth comparison of the key differences between 4-pin and 3-pin MOSFETs, exploring their configurations, functionalities, and applications in electronic circuits. MOSFET are labeled as drain, D, power source, S, driver source, DS, and gate, G. The driver source is sometimes referred to as the Kelvin source. The drain terminal connects to the high voltage side of the power supply, allowing the drain current to flow into the MOSFET when it is activated. The power source terminals provide a pathway for the drain current to exit the MOSFET while the device is in the on state. The driver source terminal forms the loop through which the gate current flows, moving from the gate terminal through the external gate resistor and back to the driver source terminal. The pins on a 3-pin MOSFET are labeled as gate, G, drain, D, and source, S. Both the 3-pin and 4-pin MOSFETs discussed in this series are based on N-channel classification, that is NMOS. Therefore, let's take a moment to review the functionalities of the N-channel MOSFET. When no voltage is applied between the gate and the source, some current flows due to the voltage between the drain and the source as shown above. Let some negative voltage be applied at VG. Then the minority carriers, i.e. holes, get attracted and settle near the silicon oxide layer. But the majority of carriers, i.e. electrons, get repelled. With some negative potential at VG, a certain amount of drain current ID flows from source to drain. When this negative potential is further increased, the electrons get depleted and the current ID decreases. Hence, the more negative the applied VG, the lesser the value of the drain current ID will be. The channel nearer to the drain gets more depleted than at the source, like in FET, and the current flow decreases due to this effect. Hence, it is called depletion mode MOSFET. In a power electronics application, the MOSFET works as a switch. It controls the voltage and current flow between the source and drain. When a drain source voltage, VDS, is connected between the drain and source, a positive voltage is applied to the drain, and the negative voltage is applied to the source. Here the PN junction at the drain is reverse biased and the PN junction at the source is forward biased. At this stage, there will not be any current flow between the drain and the source. When a positive voltage, VG, to the gate terminal, due to electrostatic attraction the minority charge carriers, electrons, in the P substrate will start to accumulate on the gate contact, which forms a conductive bridge between the two N+ regions. The number of free electrons accumulated at the gate contact depends on the strength of positive voltage applied. The higher the applied voltage, greater the width of the N-channel formed due to electron accumulation. This eventually increases the conductivity, and the drain current will start to flow between the source and drain. When positive voltage is applied at VG as shown above, then the minority carriers, i.e. holes, get repelled and the majority carriers, i.e. electrons, get attracted towards the silicon oxide layer, insulating layer, With some amount of positive potential at VG, a certain amount of drain current ID flows through source to drain. When this positive potential is further increased, the current ID increases due to the flow of electrons from source, and these are pushed further due to the voltage applied at VG. Hence, the more positive the applied VG, the more the value of drain current ID will be. The current flow gets enhanced due to the increase in electron flow better than in depletion mode. Hence, this mode is termed as enhanced-mode MOSFET. The GeneCC semiconductor G3R20MT17K is an N-channel enhancement-mode silicon carbide MOSFET with a 4-pin configuration. It has a voltage rating of 1700 volts, an on-state resistance of 20 milliohms, and a maximum drain current of 67 amperes, housed in A2247-4 package. The datasheet for the GeneCC semiconductor G3R20MT17K device recommends using a repetitive circuit to better understand its electrical characteristics. This circuit has been replicated in EltSpice to evaluate the performance of the G3R20MT17K device. The actual model of the G3R20MT17K device was downloaded from the manufacturer's website, and it was implemented in the circuit using the recommended parameters. Let's take a closer look at the Wolfspeed semiconductor C2M0045170D device. This device is an N-channel enhancement-mode silicon carbide MOSFET featuring a 3-pin configuration. It has a drain source voltage rating of 1700 volts, an on-state resistance of 45 milliohms, and a maximum drain current of 48 amperes. The device is housed in A2247-3 package. The datasheet for the Wolfspeed semiconductor C2M0045170D device recommends using a repetitive circuit to better understand its electrical characteristics. This circuit has been replicated in EltSpice to evaluate the performance of the C2M0045170D device. The actual model of the C2M0045170D device was downloaded from the manufacturer's website and implemented in the circuit using the same parameters as the 4-pin MOSFET shown earlier. The repetitive circuit was simulated in the EltSpice environment using the G3R20MT17K device as the device under test, DUT. The circuit operates with a supply voltage of 400 volts, and the G3R20MT17K functions at a switching frequency of 50 kHz, connected to a clamped inductive load of 57.6 microhenries. After running the simulation for over 40 microseconds, we obtained several waveforms. The first waveform indicates that the conduction losses of the device were calculated to be approximately 20.71 kilowatts at the initial switching instant. Additionally, the drain current reached around 67 amperes at the same moment, as illustrated in the second waveform. The third waveform displays the drain source voltage of the device. Using the same repetitive circuit simulated in the EltSpice environment with the C2M0045170D device as the device under test, DUT. Operating under the same conditions, after running the simulation for over 40 microseconds, we obtained several waveforms. The conduction loss waveform of the device was estimated to be 22.69 kilowatts at the initial switching instant. Also, the drain current reached around 67 amperes in the second waveform. The third waveform displays the drain source voltage of the device. Let's examine the primary advantage of the 4-pin MOSFET compared to the 3-pin MOSFET. The G3R20MT17K is a 4-pin MOSFET, while the C2M0045170D is a 3-pin MOSFET. A 4-pin MOSFET package offers significant advantages over the standard 3-pin package by including a separate driver source pin. This design reduces switching losses by minimizing the effects of parasitic inductance, resulting in improved efficiency and enhanced high-speed switching performance, particularly in high-power applications. According to simulation results, The conduction loss of the 4-pin G3 R20MT17K MOSFET is approximately 20.71 kilowatts, whereas the conduction loss of the 3-pin C2M0045170D is estimated to be 22.69 kilowatts under the same operating conditions. Remember to like, subscribe, and hit the notification bell. Thanks for your support.